Here we've got that the tangent lines are below, so the function lies above its tangent lines. So literally, see how the function is literally above its tangent lines? And then here in the orange, here are the tangent lines. So notice the function is below the tangent lines for each point during this interval. We're going to talk about it here in a second, but while we're looking at the picture, here, wherever we change concavity, that is what is called an inflection point. Okay, that is what is called an inflection point. So basically, let's see if I can get this to work. Yeah. So if I make, maybe, oh gosh, this is hard. Okay, oh gosh. My wrists don't move. Okay, oh boy, there we go. So let's say I've got this kind of bowl and umbrella situation happening here. Then where my fingers are meeting, that's the inflection point. That's where the concavity is changing. So right here-ish, right? For the picture, I kind of had to estimate. So here is a very crucial table that I need you to know. And it links how the second derivative and the first derivative are tied together. So, let y equal f of x be a function. For any open interval a to b, we have the following. If the second derivative is positive, that tells us the behavior, remember behavior is increasing or decreasing, of f prime, or the first derivative, okay? So that should sound familiar, because remember, the first derivative told us the behavior of f. Now recognize the second derivative is telling us the behavior of f prime. So what do you think the relationship between the third derivative and the second derivative would be? Perfect. So the third derivative would tell us the behavior increasing or decreasing, right, for f double prime, or the second derivative. So again, here if f double prime is positive, f prime is increasing. That means the derivative, or the instantaneous rate of change, is increasing. And here's the big takeaway for the second derivative test. If f double prime is positive, that means f is concave up. Okay, and then here are the different examples of the concavity. Basically, you have this bowl, and you can have the bowl in sections, right? Because that's what this picture is right here, to show you that it doesn't necessarily have to be a fluid function or graph. Remember, you can have something broken up like a rational, to where here this is concave up and this is concave down. You don't have the full bowl or the full umbrella, but again, you just have part of it, and that's enough. Because remember, up to here, you're talking about how it relates to its tangent lines. Is it above the tangent lines or below the tangent lines? All right, so then basically the opposite for f double prime. So if f double prime is negative, that means f prime, or the derivative, the rate of change, is decreasing, and f is concave down. So again, you've got the umbrella and then the separate branches if you were to split the umbrella up, okay? So again, concave down, concave up. So when we start to do our first example, remember, if the second derivative is positive, f is concave up. If the second derivative is negative, f is concave down. Okay, that's very important. Then, here we are with inflection points. So an inflection point is a point where the graph changes concavity. Perfect. So we can change concavity here at inflection points, but also notice I'm jumping ahead a little bit, but we can change concavity at vertical asymptotes as well, okay? So that leads us into the next bullet point. A graph potentially changes concavity at C for f double prime of C equaling 0, or if the second derivative equals 0, right? Again, just like I kind of tried to emphasize over and over and over again, for the first derivative test, remember this keyword is potentially. Because here, remember, in this graph, this is representing a vertical asymptote, and there's actually no function value for this c, okay? So graphs can potentially change, okay, but it doesn't mean that they have to change. So whenever you're solving, you have to keep in mind or almost do a separate kind of equation thinking when you're talking about denominators, okay? But again, I'll go into more about that soon enough. So basically, an inflection point is where you change concavity. So let me get a third page here. Ooh, this one's really cool too. Okay. I mean, well, yes, I think it's all super cool. Okay, so again, I'm linking even further how the second derivative relates to the first derivative, which relates to f. Okay, so keep these relationships in mind. So for sake of argument, I said that we are changing concavity here at -4, 3, and then also changing here at 2, 1. Who knows mathematically if that's absolutely correct, but just for sake of ease, this is what I've chosen. So now, all of these that I have here in green, or the little smiley faces with hair, okay, intervals where f is concave up, intervals where f double prime is greater than 0. What's greater than 0, aka? Positive. Good, good, good. And then the intervals where f prime is increasing. Because remember, if f double prime is positive, that means f prime is increasing, which means that f is concave up. So mathematically, when we run the second derivative test, this is kind of going to be what tells us what to do. But here, since we're using the picture is really kind of telling us what to do, and then we're just linking the other two with the picture. So on the flip side, we've got all the answers in orange. That's where we have the relation to concave down. So intervals where f is concave down from here to here, right? So that's -4 to 2. Intervals where f double prime would be negative. Okay, so that would be here. And then last, intervals where f prime is decreasing. Again, that's here to here. Why? Because remember, that's where we are concave down. Remember that these link all to the same mathematical background. It's because the second derivative is negative. So orange with orange, green with green. I'll actually move my hand out of the way so you can see what the heck I'm talking about. So the intervals where f is concave up, -infinity to -4, and then union 2 to infinity. So where is f double prime positive? The same spots. Where is the first derivative increasing? The same spots. All right, so I know what you're thinking. It doesn't appear, right? It doesn't appear that the derivative is increasing based off of the graph. Remember, that's okay, right? Remember, that's okay. That's a separate test. That's a different kind of visual picture arc you're trying to go off of. Here, remember, we're just testing the concavity. We're linking concavity to what it tells us about the other things. And then last, remember here, going back to the definition a second ago, remember this is f double prime of x equaling 0, right? So when we run the second derivative test, which we'll do in just a hot second, these were points where we would have gotten mathematically, right, in the work, that f double prime of x is equal to 0 and solving for x. So that's where there are inflection points, right? So that's kind of self-explanatory from the definition. But then remember, the second derivative is telling us the behavior of f prime. And what things do I want you to also link with behavior? So remember, yes, of course, increasing and decreasing. But then from behavior, we can tell where there are extrema. Remember, extrema are the max and mins. Could be local extrema, relative extrema, max, min. So here, we would have a local extrema for the derivative at -4 and a local extrema of, what is that? 2 for, oh, I forgot what I was saying. Ooh, sorry. So this is for f prime would have another local extrema here at 2. The other one would be at -4. Okay, this is complicated. Hopefully I can kind of smooth it out for you as the lesson goes on. But again, if you have any questions, jot them down, email me after you've watched the whole lesson. And as you've figured out by now, I'm having to kind of cut the lesson into pieces because the files just got too big. So right here in brown is where I kind of wrote like a recap. Remember, if f prime of x equals 0 tells us the max min of f. Then if f double prime of x equals 0, this tells us where f prime has a max or min. Keep this relationship in mind at all times, right? What f prime tells us about f double prime tells us about f prime. Okay, so now we're actually going to do a concrete example. So let f of x equal x cubed minus 6x squared. Find the intervals where f is concave up and where f is concave down. Find the inflection points. Okay, so remember, mathematically, our step-by-step concrete algorithmic way, again, this is called the second derivative test, is 1. First, we have to find the first derivative so that we can find the second derivative. Remember, you have to go f prime, f double prime. Then we're going to set f double prime, or the second derivative, equal to 0. Solve for x, create a sign chart, and then interpret and give the intervals, right? Give the results.